Hello, welcome to Econometrics Melody. In this video, we'll discuss about the distribution of OLS beta estimate. We know to calculate the conditional expectation of OLS beta estimate as well as the conditional variance of OLS beta estimate. And in order to calculate the conditional variance of OLS beta estimate, we assume with the condition of homoscedasticity and non-autocorrelation. And we have calculated the conditional variance of the OLS beta estimate making use of this relationship. We have transformed this, and when we assume the condition of homoscedasticity, we got this result after certain calculation. And now if we assume that the population residual term, it is normally distributed with mean 0 and variance sigma square, then from this relationship we can calculate the distribution of the OLS beta. So the conditional distribution of OLS beta, so this is also normally distributed with its mean beta and the variance sigma square x transpose x inverse. So in these expressions, it seems like all of the assumptions of classical linear regression models are in actions. The first one is related with the linearity assumption. There is a linear relationship between the dependent and independent variables, and more precisely, it advocates the linearity of the OLS beta estimate. It is clear by this relationship. And full rank condition x transpose x inverse. If x does not have full column rank, then we cannot calculate x transpose x inverse. Exogeneity of independent variable, meaning thereby the independent variable and the residual term, they are orthogonal. Their interaction should yield no unique information. And while calculating the conditional variance of beta, we have assumed a condition of homoscedasticity and non-autocorrelation, and the residual term is normally distributed, and the assumption of exogenously generated data, that is the generating process of the population residual and the independent variables, they are different. Now if we know the distribution of OLS beta, then we can perform the hypothesis testing as well. Now from this relationship we can calculate the Z score, the conditional Z score for particular beta k. So this is equal to the OLS beta minus the population beta divided by the square root of the variance of that particular beta k. As we don't know the value of sigma, we estimate making use of sample. So this is given by this formula. And we know this relationship n minus k s square divided by sigma square. This has a chi-square distribution with n minus k degrees of freedom. And when we don't know this sigma, as we estimate making use of the sample, so the J distribution, it converts into our T distribution. So in generic form, T is equal to Z divided by root under chi-square and divided by its degrees of freedom. And for our case, the Z score is given by this expression, and the chi-square, we have this value, and divided by n minus k. The degrees of freedom is n minus k, and if we operate it, we get it as and n minus k, it cancels out, so root under s square by sigma square, so this is equal to simply s sigma, and if we operate it, this is simply equal to sigma divided by s, and again sigma over here and sigma, that cancels out. So finally we are left with, and under our null hypothesis, we have this population beta case. This is equal to 0. Therefore, the individual T score associated with any particular beta k, this can be calculated as the OLS beta k divided by its standard error, and where yes, this is equal to the root under E transpose E divided by n minus k, and here this x transpose x inverse k, so this is equal to the square root of kth diagonal element of the inverse of x transpose x. Now from this result we can perform our hypothesis test as well, and if our significance level alpha, if it is equal to 5%, then if our p-value associated with the individual beta score, if it is greater than 5%, then we conclude that the population beta, this is equal to 0, that is we fail to reject the null. But if our p-value, if it is less than 5%, then we reject our null and we make decision in favor of our alternative hypothesis, that is the beta is not equal to 0. Now we have seen that if the population residual term, if it is normally distributed, then the OLS beta estimate, this has also the normal distribution. Now we want to show that OLS beta estimate, it is independent of the residual term or its function. So the function of this is actually s square, where s square is given by this value. Now let us operate it. And let us divide both the sides by sigma. And if the population residual term is normally distributed with mean 0 and variance sigma square, then E divided by sigma, this should give us the standard normal distribution. So this relationship, it is actually a function of standard normal distribution. Here epsilon divided by sigma, it is standard normal. Also we know that the residual maker matrix and E, this should be equal to E, and M, whether it is population residual or the sample residual, this should yield the same result. Now we know that n minus k s square divided by sigma square, this has a chi-square distribution with n minus k degrees of freedom. From this relationship, n minus k s square, this is equal to E transpose E divided by sigma square. So the sum of the square of the residual of the samples, we are going to replace it by the population counterpart. And we know that this matrix, the residual maker matrix, it is idempotent. We get this result. And here again epsilon divided by sigma, this is standard normal. So this is idempotent quadratic form. So our M, this is our idempotent matrix, and this value epsilon divided by sigma, this is our standard normal. So this expression, it is actually the idempotent quadratic form of the standard normal. And here this is actually the linear form of the standard normal, and this is related with our OLS beta, and this is related with our S square, that is the sample estimate of the variance of the population residual. So beta and some function of the sample residual, that is S square, they are independent if the product of these two terms, that is equal to 0. And let us write it. And we have shown here that mx, this is equal to 0. So this term should be equal to 0, because x transpose m can be written as x transpose m transpose, because m is idempotent matrix. So this should be equal to. Therefore, we can say that the OLS beta and the sample error term, they are independent, as well as the function of the sample error term, it is S square. This value is independent of beta. Now, as we know to calculate the t-score for individual beta k, so we can calculate the confidence interval as well. So population beta for individual k, the variable k, so this is actually greater than equal to or less than equal to the sample beta minus the standard error associated with this particular beta k, the x transpose x inverse, and we take the element on the kth diagonal of this x transpose x inverse, and we know this E transpose is divided by n minus k. So we take t alpha by 2 and then n minus k degrees of freedom, and we have this yes, the standard error for this particular beta bk. So this is our lower confidence interval, and for upper confidence interval we simply add this term, and alpha is our significance level. For this particular variable k, we can calculate this value, the standard error, making use of this formula. And the probability of population beta for particular variable k being greater than this term or less than equal to this term, this is simply equal to 1 minus alpha. This is our confidence level. Now let us calculate the same for the linear combinations of beta, and this is also called as a Oaxaca decomposition. Here W is the factor of constant, and if we take the linear combination of this OLS beta, this is represented by theta, we can calculate the expected value of theta. So this is equal to W transpose, and the expected value of OLS beta, this is equal to the population beta, because OLS beta is unbiased estimator of the population beta. Similarly, for variance, we make use of this formula, variance of AX, this is equal to A variance of X A transpose. So variance of theta is actually equal to variance of W transpose B. So here this is A and this is something like X. So variance of AX is equal to A, and then variance of X into A transpose. So this is equal to W transpose, and we know the conditional variance of X. So this is equal to sigma square X transpose X inverse. And when we don't know this sigma, we estimate it, and the distribution after estimation, it is our t distribution. So the linear combination of OLS beta estimate, and this is the linear combination of population beta estimate. So therefore So we have a theta. This is the linear combination of OLS beta estimate, then after minus C alpha by 2 and its degrees of freedom, and the error term, this is S square by theta. So simply we need to write ES theta. This is our lower confidence interval, then after theta plus T alpha by 2 ES theta. This is the standard error. Again, this is equal to 1 minus alpha. And we can calculate the t-score as well. So t is simply equal to the OLS beta estimate, the linear combination of it, and we divide it by root under the variance represented by ES square theta. And we can perform the hypothesis testing as well. Now we can also perform the significance of the regression test. So this is our F test, and the null hypothesis is that the beta coefficients, they are equal to 0, and our alternative hypothesis, they are not equal to 0. So F can be calculated as Fk minus 1 n minus k. So this is equal to R a square, that is coefficient of determination, divided by k minus 1, and 1 minus R square divided by n minus k. And for these degrees of freedom, if the p-value, if this is greater than 5%, when our significance level alpha is equal to 5%, and if p-value is greater than 5%, then we fail to reject the null, and if p-value is less than 5%, then we reject the null, and we conclude that the beta, at least one of the beta, it is not equal to 0, and therefore the regression model is significant. So we can perform this test as well. And as we have proved already that the OLS beta estimate and the error term or some function of this error term, that is ES square, they are independent. The conditional t statistics, so this is given by this value, and or its generic form, this is equal to j divided by root under chi square for the divided by its degrees of freedom. And here j can be calculated making use of this formula, and chi square, we have this relationship n minus ks square by sigma square. This is chi square distribution, and this is not the function of x. Similarly, z is also not the function of x, because the z is called for particular beta. We take the diagonal, kth diagonal element of this x transpose x inverse, and this z is associated with, related with beta, and this chi square, this is related with our residual term of the sample. So they are independent. That is why the marginal distribution, that is the unconditional distribution, this is not the function of x. So we can use the same t statistic and perform our hypothesis testing, as well as calculating the confidence interval for our classical linear regression model. So whether Ax, it is stochastic or non-stochastic, meaning thereby whether X is it has some random distribution and it cannot be predicted precisely, but we need to take half of the probability to make an analysis, or whether it is non-stochastic, meaning thereby it is known precisely. In either of the cases, we can perform the hypothesis testing, as well as we can create the confidence interval making use of this t statistic. But we have to make sure that the residual population residual term, it is normally distributed, or the normality assumption of the population residual, it should hold to apply this test statistic in order to perform the hypothesis testing, as well as creating the confidence interval. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.